Hey, this is Sam at nTopology. I'm one of the application engineers here, and I'm going to share with you a demonstration of some of the capabilities that nTop platform has to offer. So before we get started here, nTop platform is set up very similar to a CAD system in that in the center here is our design space. On the left-hand side is our notebook, and this is where we're going to be creating these workflows. And all of the functions within nTop platform are represented with these blocks. And it's how we embed these blocks within one another that we're going to create this optimized geometry. Up top here, we have our ribbon with some of the functions in nTop. We have these basic modeling tools here, including shelling and our Boolean functions, which are incredibly powerful and don't fail. We have our lattices tab where we have some surface-based lattices as well as our volumetric lattices. Under our simulation tab, we have a couple different simulations to offer within the platform. Right now we have linear static, modal, buckling, and thermal, as well as topology optimization. And we also offer you the ability to import stress data from another outside software if that's necessary to then further optimize your part within nTop platform. And then under our manufacturing tab here, this is where we enable you to skip the step of exporting an STL and actually just slice your final optimized geometry right in nTop platform, and then either export those slices to one of the printing companies that we are partners with, which is currently Renishaw, EOS, or Arcam, or you can export the generic CLF or CLI format. And of course, if these formats don't work for your printing methods, you can also export an STL very easily. So first, I'm going to walk you through how to create a volumetric lattice, or one way to create a volumetric lattice. So this is a brake pedal that I modeled in SolidWorks, and it's a well-designed brake pedal, but for additive manufacturing, there's a lot of material here that we don't need. So what I'm going to do is take this center body and fill this with a lattice structure. And how I'm going to actually do that is by creating a conformal lattice between this top face and this bottom face. So I'll drag my faces into my first two inputs of this lattice block. My third input is asking for what type of unit cell we want, and this is what type of lattice structure we're going to be generating. And finally, I'll define how many unit cells are arrayed in each direction. And now we have this nice lattice created in that center area of this brake pedal. So now we can apply uniform thickness to these beams, or we can take this one step further and run a stress analysis on this part. And you can imagine, you're driving in your car and a deer runs in front and you slam down on the brake pedal here. We're applying a force to this face here and then constraining these holes here where this pedal would be attached to your car. And now we can see in these red zones, these are high stress regions. And in these blue zones, this is where we have a low stress region here. So what we can do is take this heat map and apply it to our brake pedal in order to variably thicken these beams. So in those high stress regions, we have thicker beams, we have more reinforcement there. And then in these low stress regions, there's no need to waste on material cost where we don't need as much reinforcement. So we have thinner beams here. And then finally, we can slice our optimized geometry and send it off to a printer to be built. So that was one type of lattice, a volume lattice. We also have a conformal lattice to a surface. And this is an example of an iso grid here. So what we can do is bring in this surface, no matter how complex it is, apply a local coordinate system, define what unit cell we want again and how many. Now we have this nice conformal lattice here. And you can run through all these different design iterations and choose whichever unit cell that you want. And we have a number of them built into our software already. So usually when you're designing a part in CAD that you're going to manufacture, your first design is not usually the ending product. There's a lot of redesign and different design iterations along the way. An nTop platform is so helpful because, you've optimized this geometry here, but say you want to make the size of these holes much larger. Our notebooks are not set up in a linear fashion, so you can easily go back to your import part block, choose that folder where you imported your part, bring in your updated model, and it will automatically rerun this entire workflow for this new model that you've brought in. So really, we're just saying once you do the work once, you don't need to do it again. You can just reapply this workflow over and over. And on a similar note, we also enable you to actually create your own blocks in nTop platform. And what that's doing is taking an entire workflow that you've made and packaging it up into a single block. So for example here, I've made this whole workflow to shell out this impeller and then fill that void with a lattice structure. And you can see here I filled it with this nice gyroid lattice. And say I want to run this workflow, use this workflow on a number of different parts and maybe pass it along to one of my colleagues for them to use as well. But the only things that I really want to be able to change are what lattice I'm using and also my wall thickness. I can go into this workflow and pull out those specific parameters and then package up the rest of this into that block. So my lattice type and my wall thickness are the only parameters I'm going to be able to change. So now I've named this workflow shell and fill. And instead of opening up this file again, I'm going to import it into a new instance of nTop. Now I can just search for this block. And here we have shell and fill. So this is my custom block here that I've made. And now you can take any other geometry that you're looking to apply this workflow to, drop it in here. Now we're just waiting for it to render to the screen. And voila. We can reuse this workflow over and over again for any number of parts. So we also have topology optimization in our software, and this is definitely one of my favorites. It just creates really cool organic looking structures, which I love. And so what we've done here is apply our forces to this hole here and this hole here, and we've constrained these two outside holes. And now we can run through these different design iterations and watch this part grow following these stress paths, creating material only where it's necessary for this part to remain structurally sound and eliminating it everywhere else. And now what really sets nTop apart is that we have this kind of raw looking mesh result here. And in another software, you would have to go in and either individually click on each one of these facets to smoothen out this part, or just use this result as a template and redraw your surfaces over it. But because of the way that nTop was made with these math equations under the hood, representing all of our geometry here, we can just one click smoothen this result into a nice, usable part here with no manual labor necessary. Another really cool feature with nTop platform is really just being able to have full control and manipulation over our lattice structures. So I've filled up these two boxes here with this stochastic lattice. It's a very randomized lattice structure. Really great for medical products, among many others. Because you can imagine, if this isn't an implant, this is really organic and nice for bones to grow in. But here, I'm controlling based off of this plane here in this top box, the density of this lattice. So I'm saying at this plane here, I want a really, really dense lattice, tiny pore size. And then as we move away, we're linearly varying this density, moving towards a much less dense, very large pore size. And then on a similar note, on this bottom box here, we're starting with very thin beams and we're keeping our pore size constant, but we have very thin beams. And then as we move away from that plane, again, our beams are becoming thicker and thicker. And so right now I'm using this plane as this point of modification, but you can use anything here, whether it's a piece of geometry or maybe a specific surface within your part, or even stress analysis results. And just as an example of that here, I've made this shoe sole and we actually have a pressure map of someone's foot stepping down. And now you can see that I've created a more dense lattice in the zones where you can see our big toe here, where this foot is stepping down, we have more support there. And then it's a lot more less dense and airy in these other zones where we don't have as much pressure. And finally, just to show you some pretty cool surface texturing that we can do with our architected materials toolkit. And what these toolkits are, we just released them. They're basically a lot of workflows that we've found that a bunch of customers are asking us for, or that we've found we're using over and over within the company. We've prepackaged these into these custom blocks, as I showed you before. So now, say I want to blend two different lattices together. All you need to do is drop in your body into this subtractive textured lattice block and define what two lattices you want, and the work is done for you under the hood. So you can just run through a bunch of different cool surface textures here. So these are just some of the awesome capabilities that nTop has. Please email us at sales@ntopology.com if you want to get in touch with us further, and if this seems like something that would really help within your workflow for optimizing your own parts within your business. Thank you.